இப்போ ஜாயின் பண்ணு இன்டர்நெட் வேலை செய்யணும் கம்ப்யூட்டர்ல All right, so we will begin the online lectures of limit process again today. So last time we talked about the limits of a sequence, and we see how we can compute a limit of a sequence by using the basic definition for limit, right? The epsilon definition, and then we define what do we mean by limit n goes to infinity in a for a sequence. So now what we are going to do is we're going to see an example of a limit which goes to infinity, right? Especially for minus infinity, and then we will talk about some other properties of limits. So I will begin with an example. Right, so this question is about limit, right? Limit of 1 minus n when n goes to infinity is equal to minus infinity, right? So we want to show that. So basically you want to show that you have a negative number such that 1 minus n is less than that negative number for all natural numbers larger than certain n, right? So you know that you have to show that is less than k, right? Where k is a negative number for all n greater than n, right? So this is what you want to show. So here your xn is 1 minus n, right? So you want to show that 1 minus n is less than k. So basically, you want to show 1 minus n is less than k. This is what you want to show, right? So basically, you will have to simplify this. You get 1 minus k is than n. So this line can be obtained by using the Archimedean property, right? So we already saw that we can define certain conditions by using the Archimedean property. So here, what I'm going to do is I'm going to start with, let k be a negative number, right? So if k is negative number, then right, then by Archimedean property, right, you know that there exists a natural number such that 1 minus k is less than n. Because k is negative, so 1 minus k is positive. So you can always find a natural number less than that. Right? So that means, right, for all n greater than n, for all little n greater than n, you know that 1 minus n is less than 1 minus capital N, right? So that's obvious. The inequality property you studied earlier, right? But 1 minus capital N is less than k. So that is enough to show that the limit n goes to infinity, 1 minus n is minus infinity, right? So what you do is, right? So this is what we show. For all k greater than 0, there exists a natural number n such that 1 minus n is less than k for all n greater than n. So that is what we have as the definition for limit n goes to infinity is equal to minus infinity. So this is how you show infinite limits, right? So when limit goes n goes to infinity, when the limit is minus infinity or plus infinity, you can show it in this way. So I will write down an exercise for you to work out a similar idea. And so you want to show limit n goes to infinity, a to the power n is equal to positive infinity, right? So that is a similar type of exercise. So you need to, again, by using an Archimedean property, you have to show that this time for some positive k, a to the power capital N greater than k. That is what you want to show, right? So then you can always build up a inequality from that, right? So basically the inequality leads to Archimedean property. So that you can do. Right. So now what we are going to do is we are going to define something else, a new property of a sequence. Right. So this is a homework. Right. So we are going to define something called bounded sequences. Right. So what do we mean by a sequence is bounded? So that means, right, so when we talk about real numbers, we talk about interval or set of real numbers is bounded above and bounded below in the previous chapter, right? So when we try to define supremum and infimum, we say that a set of real numbers is bounded above and a set of real numbers is bounded below. And if it is bounded above and bounded below, then we call it bounded and things like that we say, right? So there we say that a set is bounded above if every element is in the set is below a certain number. So we say that the set is bounded below if every element in the set is above a certain number. So here the same kind of definition we are going to do for sequences, right? So you know that sequences are basically, right? So you are going to have, it's going to look like that, right? So this is how you are going to have sequences. For n is equal to 1, you will have one person, n is equal to 2, another, 3, another, 4, another, like that. You are going to have sequences, right? So some of them may go to 0, some of them may go to some number, some of them may go to infinity, some of them goes to minus infinity, and so on, right? So we have seen these examples already, right? So based on that, we are going to define boundedness of a sequence. Right, so first we say a sequence is bounded above, right, if there exists a b, right, such that xn is less or equal to b for n, right? So if the sequence, the range of the sequence is less than a fixed real number, right? So less or equal a fixed real number, right? So this b is a real number, and that is true for all n, right? So for all values, if the value of the sequence stays below a certain number, then we call it as a bounded above sequence. So similarly, bounded below, if there exists b belongs to real number such that xn is greater or equal to b for all n, right? So if the values of the sequence stays above a certain value, then we call that sequence as a bounded below sequence. So if it is bounded, right? So if it is bounded, right? So then it should be bounded above and bounded below. Right? So it is bounded above and bounded below. Right? So then we call it bounded. Usually, that's how we call bounded. But generally, this is how we write. Right? So bounded, if there exists a number m, right, which we call it as a positive number, right, such that right, the absolute value of xn lies between is smaller than some fixed value m, right? So then we call it as a bounded sequence, right? So generally, if it is bounded, obviously you know it should be as bounded above and bounded below. But in general, this is how we define a bounded sequence. Right? If absolute value of the range of the sequence is less than a fixed positive number m, then we call it as a bounded sequence. Right? So let me write down a few examples. Okay, so example one of the sequences examples we did 1 upon n, right? So the sequence 1 upon n. So you know that absolute value of xn is absolute value of 1 upon n, that is 1 upon n, right? Look for absolute value of xn. So here in this sequence, absolute value of xn is 1 upon n. And you all know that for all n belongs to natural number, 1 upon n is less or equal to 1. Right? Because 1, 1 upon 2, 1 upon 3, 1 upon 4, and so on. Right? So for all natural numbers n, 1 upon n is less or equal to 1. So we call it, so the sequence 1 upon n is bounded. So it is bounded. Similarly, another example, right? So 1 upon minus 1 to the power n. And so this is again the sequence we saw, right? But we already show that this sequence does not have a limit, right? But here the absolute value of minus 1 to the power n, right? So if n is odd, it is minus 1, and if n is even, it is plus 1. But when you take the absolute value, it is always plus 1. So this is always plus 1. And you all know that this is less or equal to 2 for all natural numbers. So clearly, this one is also a bounded sequence. Okay, so this is how you define bounded sequences. Right? So another example I'm writing as an exercise, xn is equal to minus 1 to the power n over n. Right? You try to see whether this one is bounded or not. Okay, now we are going to talk about the important property of a sequence, which is known as convergence of a sequence. Right? So whenever you have a sequence, right? So we see that the sequence may have a limit, right? Sometimes the sequence may not have a limit, right? Sometimes the limit is minus infinity, sometimes the limit is plus infinity. We have seen all possibilities there, right? So we have seen the sequence, and then we have seen example for that, and then we see when limit n goes to infinity, the sequence goes to some number, right? And then we see that when n goes to infinity, the sequence does not goes to a number, so that does not has a limit. And then today we see when n goes to infinity, a sequence goes to plus infinity, and we see when sequence goes to n goes to infinity, the sequence goes to minus infinity, right? So these are all the possibilities we have seen. Based on this, we are going to define the convergence of a sequence, right? So this is one of the important properties of the sequence, the convergence and divergence. It is the opposite of convergence. Okay, so right, so we call a sequence as a convergent sequence if the sequence has a finite limit. So we have seen examples. Sorry, 0. Boundedness is 1, limit is 0, right? So this example we did, limit of n goes to infinity, 1 upon n is 0 is something we have seen. Example. So clearly, you know that the limit exists and this limit is a finite number, right? So it is a number which is known, right? It is a finite number, right? Infinity are the infinite numbers, all the others are finite numbers, right? So here, this sequence has a finite limit. So we say that the sequence 1 upon n is convergent. 1 upon n is convergent. Similarly, you know that limit of n goes to infinity, n over 2n plus 1, right? So this is another example we see earlier, right? So limit of this sequence. And we have seen that this is equal to 1/2. Right? So this is again a finite number, right? So right, instead of writing conversion, we usually just to save time we write CGT, right? So that is a abbreviation for conversion which we will use in this notes, right? So not in general, but in this notes we will use CGT just to abbreviate the big word conversion, right? So as long as the sequence has a finite limit, right, we call that sequence as a convergent sequence, right? So obviously the other type of limit is infinity limits, right? Then it should be the opposite of convergent, right? If the limit is infinity, right, plus or minus infinity, then it should be opposite of convergent. So we call it divergent, right? So right, so the sequence is convergent if it has a finite limit, right? If it has an infinite limit, right? Right, so if it is the plus infinity or minus infinity, right? So if it is plus infinity or minus infinity, right? So if the limit of the sequence is plus infinity or minus infinity, then we say that the sequence is divergent, right? So that is another type, right? So you know that example, limit of n goes to infinity, n is infinity, right? So clearly that sequence is divergent, right? So other example is limit of n goes to infinity, 1 minus n, we say that it is minus infinity, right? So clearly these sequences, right, minus infinity and plus infinity, right? So the sequence n is divergent. And so here also the sequence 1 minus n is divergent, right? So DET is again the abbreviation we will use to denote divergent, right? So these are two important concepts or properties of sequences, right? So one is convergent, the other one is divergent. So you should be very familiar with this, right? So if the limit of the sequence is a finite value, then we call the sequence as a convergent sequence, right? So if the limit of the sequence is an infinite number, right? So it's plus infinity or minus infinity, then we call that sequence as a divergent sequence. Right? So there is other case, right? Which an example you see minus 1 to the power n, right? So that is the sequence which does not has a limit, right? It is not a finite number, it is neither an infinite number, right? It is all just the sequence does not have a limit. Minus 1 to the power n is a very good example, right? So that sequence does not has a limit. So what kind of property that kind of sequence will have, right? So we call that as an oscillating property. Right, so we call that sequence as an oscillating sequence. Right. So you have limit of a sequence does not exist case, right? Earlier, minus 1 to the power n is a very good example of that. Right? And again, when we see minus 1 to the power n, we have seen that that sequence is bounded, right? Minus 1 to the power n, absolute value is always less or equal to 2, right? So we already see that. So that means that sequence is bounded, but the limit does not exist. So that kind of sequences, we call it finitely oscillating, right? So example, minus 1 to the power n, right? So we already see that it does not has a limit, and we already see that the sequence is bounded. So now, what is infinitely oscillating, right? And so infinitely oscillating, we have finitely oscillating, so opposite of that should be infinitely oscillating. So we will see what do we mean by infinitely oscillating. So again, limit does not exist. Right? D and E means does not exist. Right? Limit does not exist. At the same time, sequence is unbounded. Right? So the sequence is unbounded. One example is minus 1 to the power n multiplied by n. And so you can see that absolute value of this number is n, which is unbounded, right? But limit of the sequence also minus 1 to the power n will not exist, right? Because it will go from minus infinity to plus infinity and minus infinity to plus infinity. So these are the four types of convergence properties which we can have on a sequence, right? So let me draw some pictures to tell you what do we mean by finitely oscillating and infinitely oscillating and stuff like that. Okay, so you see that right? So xn is equal to 1 upon n, right? So you can see that 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, like that. The sequence will, right, converge to 0, right? So if you draw the picture of 1 upon n, right, over n, then you can see that it is a sequence which will converge to 0. Right? Similarly, if you draw the picture of xn is equal to n, so 1 is 1, and 2 is 2, 3 is 3, 4 is 4, 5 is 5, 6, right? So here in this thing, you can see that the pattern is going like this, so which says it is going to 0. But here you can see that the pattern is going all the way to positive infinity. So this is a converging sequence. It is converging, right? So it is coming towards to a number, right? Here this is called a diverging sequence because it's going away towards plus infinity, or it is going down all the way to minus infinity, right? So this is how graphically you can see the converging and diverging sequence. Right? Oscillating sequence, which I drew last time also. Right, so oscillating sequence. Right, so xn is equal to minus 1 to the power n, right? So you know when n is equal to 1, it is minus 1, 2, it is plus 1, minus 1, plus 1, minus 1, and plus 1, and it will go like this. Right? So you can see that, right? So it is going on a zigzag line, but it stays between two lines, right? So it is oscillating between two fixed values, right? So that is why we call it, it is finitely oscillating, right? So it is oscillating, it's like a pendulum, it is going up and down, but it stays in between two lines. The other example, right? So xn is minus 1 to the power n times n. Right? So when you put n is equal to 1, you have minus 1. Right? N is equal to 2, you have plus 2, right? Because n is equal to 2, 1 times 2 is 2. And then when n is equal to 3, you have minus 3. And then you have plus 4. And then you have minus 5. Right? So now you can see that here in this case, the sequence is going from here to here, to all the way here, to all the way here, going all the way there. So here you can see that it is oscillating, right? But it is expanding as n gets larger, right? Here it is oscillating, but it does not expand. It is the same shape, right? So here you can see that it is oscillating. At the same time, it is expanding as well. So that is how pictorially you can see the convergent sequence, divergent sequence, oscillating, finitely oscillating sequence, infinitely oscillating sequence, right? So if you have these pictures in your mind, right, you can easily see the definition of the convergence sequence, right? So if you have this picture, you know that, okay, the sequence should goes to a finite limit. If it's a divergent sequence, if you have this picture in the mind, you say, okay, the sequence goes to an infinite limit. Oscillating, finitely oscillating, okay, should goes up and down, so no limit, but bounded, stays in between two values. Here, infinitely oscillating, so going up and down, no limit, and expanding, no bound as well. So that is how we define the four types of convergent cases in a sequence of a sequence. So now we will start doing some theorems or problems related to this, right? So the first of those theorems is every convergent sequence is bounded, right? This is where the big theorems and important theorems are going to come in, and I will just write the theorem. Right, so we are going to show that convergence implies bounded, right? So every convergent sequence is bounded, right? If I want to write it here, right? So every convergent sequence is bounded, right? So that is what we are trying to prove first, right? So you know that you have to take a convergent sequence and you have to show that it is bounded, right? So if it is a convergent sequence, then you know it will have a limit, right? But you want to show that boundedness is xn, absolute value of xn is less than some number. Is what you want to show bounded, right? So here you know that, right? Limit of xn is equal to L. From this, you have to show that xn is less than m, right? So this is what you want to show. You are given this, you want to get here, right? So as usual, we will start with the definition of limit, right? So okay, so limit xn is x is and finite, so we call it L. So let us name this as L. So you write the definition for limit, right? Okay, right. So this is true for all epsilon greater than 0. There exists n belongs to natural number such that xn minus L is less than epsilon for all n greater than n. That is the definition for limit. So now what we are going to do is we are going to fix, right? We are going to fix epsilon is equal to 1, right? Just for simplicity, let us fix epsilon equal to 1. Then, right, there exists n1 belongs to natural number such that xn minus L is less than 1 for all n greater than n1, right? So you know that. So when you fix n, yeah, so when you put epsilon is equal to 1, you have to have a fixed n1, so that we can call it n1, right? But you know that a consequence of triangle inequality, which we studied on the first chapter, right? The first chapter we studied this results after triangle inequality. Absolute value of xn minus absolute value of L, absolute value is less than xn minus L. So clearly, you know that, right? So absolute value of xn minus absolute value of L is less than 1, right? Because this one is less than 1. So from this absolute value of this less than 1, so that will be between plus or minus 1. So you take only less than plus 1 case. So this says there exists n1 belongs to natural number such that xn is less than 1 plus absolute value of L for all n greater than n1. Okay, so we have for every n greater than n1, there exists, so for some n greater than n1, for all n greater than n1, xn, absolute value of xn is less than the fixed value 1 plus absolute value of L. So now we have boundedness for the sequence above the points xn plus xn1 plus 1, xn1 plus 2. Right, so if you look at this picture, right, so here up to this n1, the sequence may be somewhere here like this, right? But here we call it after n1, the sequence is between these values, right? Absolute value of xn is less than 1 minus 1 over 1 plus absolute value of L, right? So boundedness is proven after this. But to prove boundedness, you have to prove this one also bounded. So in order to do that, what we are going to do is we are going to so what we do is, in order to say that here also it is bounded, right? So we take the maximum of the values x1, x2 up to xn1, because up to xn1 is the problem you have, right? So up to xn1 you take the maximum among the sequence values, and then all the others are between the absolute values less than 1 plus n. So you take the maximum among all of them, right? So the maximums of here and maximum of here. So then m will be these two lines, right? So m is the range between these two. So clearly, right? So because m is the maximum of these, so x1 will be less than or equal to m, right? So and x2 will be less than m, right? And x3 will be less than m, right? And then x4 will be less than m, xn1 is less than m, xn1 plus 1, xn1 plus 2, and all of them is less than 1 plus L. So it should be less than n, right? So this is how you prove the boundedness of the thing, right? So that concludes the boundedness. So we will stop here, and in the next class we are going to see some more properties of a convergent sequence, right? So because convergent sequence is the one which has more interest on that, so that we will see here. And for the question about the video in the LMS, we cannot post the videos, right? So because these videos are 1 hour and LMS cannot have this, so we will upload lecture notes in the LMS. And what we are going to do is we are going to upload the video on the Google Drive and share you the link on the LMS, so that you can click on the link and look at the video whenever you have internet connection, right? So that we will do, but we will not put the video on the LMS. We will put only the link for the video on the LMS, and we will put the lecture note for chapter 2 as well on the LMS, right? So, and we will continue this class on the next class time, which will be Tuesday 1 o'clock, right? So we will stop here.